Hi, this is a course on electromagnetism, and in this lesson, we're going to discuss about the capacitance, current, resistance, electromotive force or your EMF, and your Kirchhoff's rule, which some people read this one as your Kirchhoff's rule. And in this video, we are going to first discuss about your capacitors and capacitance. So what are capacitors and what's capacitance? Any two conductors separated by an insulator form a capacitor. This insulator will allow the electric field between the conductors. However, the insulator will not allow the charge to flow from one conductor through itself to the other. Above here are some of the images of your common capacitors, which you can see in your circuits, your electronic circuits. Okay, so these are your different capacitors. The more charge you can hold, the larger the capacitor, or the larger your capacitor, the more capacity to store your charges. And you can charge the capacitor by pushing it there with a potential voltage. And you can actually just say that you apply some pressure so that your charges will be pushed into your capacitor. This is how you're going to charge a capacitor. So you just simply connect your capacitor with a battery, and then this battery here will push your charges into your capacitor so that your charges will be stored here. The definition of your capacitance, C, is equal to your Q divided by BAB. Here, Q is the charge stored that we are talking about earlier, and your Q is in coulombs. And Q is held symmetrically on each plate, on each two plate. So on one side you have plus Q, and then on the other plate you have negative Q. And this symbol here, wherein you have two parallel lines, and then you have this lines here on both sides, which represents the wire. These lines here represent your capacitor. This is the symbol which we are going to use when we are now going to embed your capacitors in circuits. So you have to remember this symbol here. Potential difference BAB is the electrical pressure that pushes and keeps the charge there. This is your BAB. And so here you have your capacitance C, that's equal to your charge stored divided by your potential difference BAB. Now, C is equal to Q over BAB, so that means your Q is equal to your capacitance times your potential difference BAB. Q increases as C is made larger for a given pressure. That means you have more Q that can be stored when you have a larger capacitor, or uh, you have more capacity means more charge stored. And Q also increases as your potential difference, or as the voltage that you apply increases. And for any particular capacitor, more pressure BAB allows it to hold more charge. But no voltage applied means no charge stored. Of course, if this is zero, if you do not apply some voltage there, or if you do not connect your capacitor to some circuit, then there is no charge stored. So you have here again your capacitance. And what's the unit of your capacitance? It's in farads. So your Q is in coulombs, and then your VAB, or your potential difference, is in volt. So you have the units of your capacitance, which is in farads. It tells you how much charge can you store per joule of work to keep them there. But remember that your volt is just equal to your joules per coulomb. So that means your farad is actually equal to also coulomb squared per joule. Now we talk about your capacitor, and we've said that your capacitor store charges. Now, batteries also store something, right? So what's the difference between your capacitor and then your battery? Your capacitor stores the potential energy in the electric field, whereas your battery, the potential energy is stored in the form of chemical energy, which is later converted to electrical energy. Another major difference between your capacitors and batteries is that batteries store more energy for longer times, but take more time to deliver it or be recharged. And we can say that your battery has a permanent charge storage. Whereas your capacitors store less energy, but deliver it instantly and recharges quickly. And we say that your capacitors are your temporary charge storage. Again, your batteries are your permanent charge storage. It stores more energy. However, it takes more time for your battery to deliver energy, whereas your capacitors, they store less energy, but they deliver it instantly and recharge quickly. And your capacitors, again, are your temporary charge storage. These are some of the types of your capacitors. You have your film dielectrics, your wet electrolytic capacitors, your ceramic capacitors, your polymer capacitors, you have your supercapacitors, and then your graphene. So in today's generation, we are actually doing researches on your supercapacitors and then graphene. Graphene is a two-dimensional carbon allotrope of honeycomb shape, and we're still actually on the study of using graphene for your capacitors. Now this is how your capacitors look like. So you have two metal foil, and then in between sandwich is your insulator, which is in this case here is your dielectric film. Okay, and this is how we picture out how we make a capacitor out of your graphene. Capacitors have tremendous number of practical applications in devices such as in electronic flash units for photography, your pulse lasers, airbag sensors for cars, and radio and television receivers. An example of where you use your capacitor is in camera flashes in photography, and this is how your camera flashes works. So basically, you have three major parts. You have a small battery, which serves as the power supply, a gas discharge tube, which actually produces the flash. So you have here a typical camera flash tube removed from its housing, and this looks like a miniature neon light. And then this flash tube sits in front of the trigger plate. So you have this trigger plate here, and this trigger plate is hidden by reflective material which directs the flashlight flow forward. And the third major part is a circuit made up of a number of electrical components which connects the power supply to the discharge tube. And one of the component of your circuit is a capacitor, which basically here stores your charges, which was taken from the battery or which was pushed there by the battery. And what happens is that your capacitor again it temporarily stores your charges, and when you're going to click the clicker in your camera, the charges stored in your capacitor will then be discharged up to your tube. Okay, so that's the purpose of your trigger plate there. And what happens is your charges will ionize the gases in your tube, which is actually composed of your xenon gases. And your xenon gases, when ionized, they create flashes of light. And when you're going to unclick the clicker of your camera, your your circuit will now again back to store charges back into your capacitor. We normally model your capacitor with a parallel plate capacitor. Here you have two parallel plates, okay, of area A, and these two plates here are separated by some distance d, and here you have your potential difference, okay. So your plates, they store your charges depending on how you're going to connect your power supply or your battery. So we may have a configuration wherein the above plate stores positive Q charges, and then below you have your negative Q charges. And the capacitance of a parallel plate capacitor is equal to your C. C here is your capacitance. This is equal to epsilon naught, your permittivity of free space, times the area of your plate, divided by B, which is the separation distance. And looking at the side view of your parallel plate configuration, this is what happens in your electric field lines. Okay, so here you have your above plate, you have your positive Q, and then below you have your negative Q. So since the above plate has positive charges and below you have negative charges, your electric field lines flow from your positive towards your negative. And when the separation distance d is very small compared to the size of your capacitors, the fringing of the field is uh, light. So this is your fringing here. So again, the capacitance of a parallel plate capacitor is equal to your C. That's equal to epsilon naught A over D. And as you can see from this equation here, you can actually engineer your capacitance C. So C can be engineered, and you can do this by controlling the area and the distance of your design. So as you can see from your equation, your capacitance increases with your area. So the larger your area of your plates are, the larger is your capacitance. And your capacitance decreases with your separation. If you're going to increase the separation distance of your two plates, the capacitance of your capacitor decreases. So if you want to make your capacitance up to the maximum, you need to decrease this separation distance d here. And increasing your capacitor, you may make your uh, the plates, the size of the plates, be very, very large. So we just use this equation here in order to modify the capacitance of your capacitor. So it's just from your C that's equal to epsilon naught A over D. In using the capacitance equation, your C that's equal to epsilon naught A over D, we're going to use here a different unit for your permittivity of free space. So if you want to uh, if you play with the equation, that is, if you take out your epsilon naught is equal to your capacitance times your distance over your area. Your capacitance is measured in farads, your distance is measured in meters, and then your area is measured in meters squared. Therefore, as you can see, your epsilon naught here has units of farads per meter. Recall that your epsilon naught from your Coulomb's law is equal to that's equal to your force is equal to 1 over 4 pi epsilon naught q1 times q2 over r squared, and the unit here of your permittivity of free space epsilon naught is in coulomb squared per newton dot meter squared. So as you can see, your farad per meter, the unit that we are going to use for your parallel plate capacitor in this equation, is equal to your coulomb squared per newton times meter squared. And farads, it's just equal to your coulomb squared per newton dot meter squared, and or newton, sorry, it's newton meter. And as you can see, your farad is equal to your coulomb squared per joule. So since this one here, your newton meter is just in joules. So let's have an example. This is still about your parallel plate capacitor. The plates of a parallel plate capacitor in vacuum are 5 millimeters apart and 2 meters squared in area. So as you can see here, the separation distance is a very small scale. It's in millimeter and your area is in meters. So it's a very large area compared to the distance between the plates. A 10 kilovolt potential difference is applied across the capacitor. Compute the capacitance, the charge on its plate, and the magnitude of the electric field between the plates. So with these dimensions of your capacitor, we are asked to compute for the capacitance, the charge on its plate, and the magnitude of the electric field between the plates. So let's solve first the capacitance. So the capacitance C is equal to epsilon naught A over D. And here your epsilon naught is just 8.85 times 10 to the negative 12 farads per meter. Your area, 2 meters squared, divided by your distance, which we need to convert into meters. That's equal to 5 times 10 to the negative 3 meters. So this is just straightforward. And we get a capacitance of equal to 3.54 times 10 to the negative 9 farads. Or that's equal to 0.00354 microfarads. As you can see, even if you have this large area of your parallel plates of 2 meters squared, you still have this very small capacitance in your capacitor, which is just around 0.0354 microfarads. If you want to have a bigger capacitance, you either increase this one or decrease this distance D here. And if you take note, if you're going to buy a capacitor in stores, you'll see that the units of your capacitor is very small. So you buy capacitors of microfarads, picofarads, or even in nanofarads. If you want a capacitor of farads unit, that would make your capacitor a very, very large one. Now let's solve for the charge on each plate. So the charge on each plate is just given by your Q, that's equal to C times VAV, where again your C is your capacitance and then your V is your potential difference. We have solved the capacitance earlier, and we found it to be around 3.54 times 10 to the negative 9 farads, where again, if you remember from the previous discussion, your farads is just equal to coulombs per volts. So you have 3.54 times 10 to the negative 9 coulombs per volts times your potential difference, which is 10 kilovolts, and we just change it to the standard units in volts. So that's 1 times 10 to the 4 volts. This is straightforward, and we can solve this one easily, and we get your charge that's equal to 3.54 times 10 to the negative 5 coulombs, or that's equal to 35.4 microcoulombs. The plate at the higher potential has a charge of plus 35.4 microcoulombs, and then the plate on the lower potential has a charge of negative 35.4 microcoulombs. So finally, let's solve for the magnitude of the electric field between the plates. The magnitude of the electric field between the plates is just your E. It's equal to your sigma, which is your surface charge density over epsilon naught. Your surface charge density, it's equal to your Q over your A. So your electric field magnitude is Q over epsilon naught A. So we have already solved for your Q, and then you have here your epsilon naught times your area. This is again straightforward, and you can see that solving this one, you get an electric field magnitude of equal to 2 times 10 to the 6 Newton per Coulomb. Capacitors are manufactured with certain standard capacitances and working voltages. Say, for example, if you're going to buy your capacitors in your electronic shops, you'll see that there are actually just specific capacitances and working voltages for your capacitors. Like, say, for example, these capacitors here. Common capacitances are in 330 microfarads, or you have 110 microfarads. And however, these standard values may not be the ones you actually need in a particular application. Like, say, for example, when you're going to simulate your electronic circuit and you find that you want a capacitance that is exactly 143, let's say 143 microfarads, you cannot just buy a 143 microfarads in your electronic shops. And you can simply obtain these values that you need by combining capacitors. Many combinations are possible, but in this lesson, we're going to discuss the simplest combinations, which are your series connection and then your parallel connection. So here, this is an example of your series connection, wherein your capacitors are just connected in series, and this is for your parallel connection. So as you can see, your capacitors are connected in parallel with each other. So let's discuss first your capacitors in series. Capacitors are in series if your capacitors are connected one after the other. Like say for example this one here. So you first have your first capacitor and then after that one you have directly another capacitor. So this is a series because your capacitors are connected one after the other. And for capacitors in series, the capacitors have the same charge Q. So you need to take note of this one. They have the same charge Q. And their potential difference is the sum of the individual uh, potential difference of your capacitors. That is, if in this segments here, you have a potential difference of VAC or V1 for your capacitor 1. And for your capacitor 2, on segment BC, you have potential difference of VCB, or let's say you have a voltage V2 for your capacitor 2, then the potential difference of this circuit is just equal to the sum of the individual voltages of each capacitor. So you have your V1 plus V2, that is your voltage AB from terminals A to B. And as you can see, again here, let's emphasize here that these capacitors in series have the same charges. That is, the charges are the same on all the plates in the series, even if you have here different capacitances. So if your capacitors are in series, they have the same charge Q. And what is different with this one is your or are there potential difference. So they have the same charges, but they have the same potential difference. Okay, even if they have again different capacitances, they will still have the same charge Q. And what's different with them is their potential difference. Now these two capacitors here, which are in series, can actually be thought of as just a single capacitor. The equivalent single capacitor for these two capacitors here will look like this one here. So you just have one equivalent single capacitor for these two capacitors. And here the charge is the same as for the individual capacitors. Again, earlier we've said that these two capacitors have the same charge Q. And if we just have one equivalent single capacitor, we still have the same one or the same charge that is the same as for the individual capacitors. And for this case here, since we combine your two capacitors into one, you have what we call your equivalent capacitance, which is less than the individual capacitances. And the equivalent capacitance of a series combination of your capacitors is given by this equation. So you have 1 over C equivalence, that's equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus up to how many capacitors that you have in your circuit. So this is for your capacitors in series. And in order to get your C equivalence, you just take the reciprocal of your 1 over CQ, and then you get the equivalent capacitance of your circuit. For this case here, so we have two capacitors, your C equivalence is equal to your Q over B. That's and you get your C equivalence from 1 over 1 over C equivalence. That's equal to 1 over C1 plus 1 over C2. Okay, and you can get the voltage of your the voltage from A to B just from this equation here. So you have C equivalence that's equal to Q over your B. So we have here again the equivalent capacitance of a series combination. And you just take note here that your C equivalence is always less than the smallest capacitor in series. Say, for example, you have the following capacitors. You have C1 that's equal to 10 millifarads, C2 20 millifarads, and C3 30 millifarads. And if we combine these three capacitors in series, you get a C equivalence that's equal to 1 over CQ. That's 1 over 10 plus 1 over 20 plus 1 over 30. you get 1 over C equivalence is equal to 11 over 60. And we get the reciprocal of this one. So your C equivalence is equal to 60 over 11, or that's equal to 5.45 millifarads. And again, your smallest capacitance is 10 millifarads, and this equivalence that we get is just 5.45 millifarads. And you see here that your C equivalence is less than the smallest capacitance in your capacitor in series. On the other hand, capacitors are connected in parallel between your terminals A and B if the potential difference VAB is the same for all capacitors. So for this case here, this is your two capacitors that are connected in parallel. So for your capacitors in parallel, the capacitors have the same potential V. And the charge on each capacitor depends on its capacitances. That is, if the capacitance of this capacitor is C1, you get the charge Q1, that's equal to C1 times V. And for the second capacitor, if the capacitance is equal to C2, then the charge on this capacitor is equal to Q2, that's equal to C2 over B. And again here, for your capacitors in parallel, what we have here is that the capacitors have the same potential V. So they are different from your capacitors in series, where your capacitors in series have the same Q. Here, your capacitors in parallel have the same potential V. And these capacitors have the same potential V. That is because at this size here, okay, these are actually just equipotential surfaces. So since these are equipotential surfaces, then that means these capacitors here are of uh, uh, the same potential. So that's why they have the same potential V. So just like what we did in your capacitors in series, these two capacitors connected in parallel can be thought of as just one single capacitor. And the equivalent single capacitor for these two capacitors in parallel can be thought of to be just like this one, just a single capacitor. And here, the equivalent capacitance of a parallel combination is just the sum of the individual capacitances. That is, your C equivalence is equal to C1 plus C2 plus C3. And for example, for this case, you have two capacitors, C1 and C2. The equivalent capacitance is equal to C equivalence, that's equal to C1 plus C2. And for the charge Q, the charge is just the sum of the individual charges of your capacitor. So if the charge of your capacitor 1 is Q1, and then for your Q2 is, or for your C2 is Q2, then the charge of this equivalent single capacitor is equal to the sum of the individual charges. That is, the charge Q of this equivalent capacitor is equal to Q1 plus Q2 of the two uh, combined capacitors. So again, remember that in your capacitors in series, you have the same charge Q. And then for your capacitors in parallel, you have the same voltage for your capacitors. So again, what you have here is the equivalent capacitance of a parallel combination, which is the sum of the individual capacitances. And take note here that the C equivalence is always more than the largest capacitor in parallel. Say for example, again, we go back to our three capacitors. Three capacitors example, you have C1 10 millifarads, C2 20 millifarads, and C3 30 millifarads. The C equivalence is just the sum of the individual capacitances, that is 10 plus 20 plus 30. So you get C equivalence of equal to 60 millifarads. And you see here that the C equivalence is more than the largest, which is 30. Okay, so it's always more than the largest capacitor in parallel. So let's have an example. So This is an example of a capacitor in a network. So find the equivalent capacitance of the 5 capacitor network shown in the figure. So here we have 5 capacitors. You have a capacitor of 3 microfarads, a capacitor of 11 microfarads, another of 12 microfarads, and then you have 6 microfarads, and then another one of 9 microfarads. So here we are asked to find for the equivalent capacitance of your capacitor network. So let's solve this problem. In finding for the equivalent capacitance of your capacitor network, our goal is to simplify your network into just one single capacitor. And to do that, the technique is you have to simplify first those networks which are much easier to simplify. Like say for example, for this case here, you're going to look at your network. You'll see here two capacitors that are in series, which you can simplify directly. It will be hard if you're going to simplify, like say for example, these two first, because you are affecting this one here and even this one here. In the same way, if you want to simplify this one here, you can do it. You have two parallel capacitors, but later on you are again going to have to simplify this one, which are also in parallel. So taking it easy, taking the easier path, we can simplify this one first, these two capacitors in series, and then after that, we do the next steps. So your 12 microfarads and then your 6 microfarads capacitor are in series. So to find for the equivalent capacitance, you have 1 over C prime. Let's just use your C prime for this moment because this is not yet your final equivalent capacitance. You 1 over C prime is equal to 1 over 12 microfarads plus 1 over 6 microfarads. And this is equal to 1 over 4 microfarads. Okay, so that's your 1 over C prime. To get for your equivalent capacitance, we take the reciprocal of this one, okay, which is your C prime. So that's equal to 4 microfarads. So what we have here for your two capacitors in series is a single capacitor, which you can combine this as it's just a single capacitor of charge or of capacitance for microfarads. So next we have this one here, which we have used to replace your two capacitors earlier. So we now take this network and we're going to simplify this one, and the next easiest network that you can combine are these three here, which are in parallel. So for parallel connection, you have let's combine this and let's label it as your C prime prime or your C double prime. That is just the sum of the individual capacitances. So you have 3 microfarads plus 11 microfarads plus 4 microfarads, and this is equal to 18 microfarads. And that is your C double prime or the equivalent capacitance of these three capacitors here, which we can thought of as just this one here. And now we are left with just two capacitors, your 18 microfarad, which is a combination of these three capacitors here, and then lastly your 19 microfarads. So now we're just left with two capacitors in your network. You have your 18 microfarad capacitor and your 9 microfarad capacitor. And you see that for this network, these two capacitors are just in series. And you can replace these series capacitors by an equivalent capacitor. And to show or to solve it, let's These are just two capacitors in series. So we have 1 over C equivalent is equal to 1 over 18 microfarads plus 1 over 9 microfarads. 1 over C equivalence is equal to 1 over 6 microfarads. And then we just get the reciprocal of your 1 over C EQ, and your C equivalent, this is equal to 6 microfarads. And we have replaced your 5 capacitor network into just one capacitor, one equivalent capacitor, which has a capacitance of equal to 6 microfarads. Let us review what we did to your capacitor network. So again, we begin with this 5 capacitor network, which is composed of your 3 microfarad, 11 microfarad, 12 microfarad, 6 microfarad, and 9 microfarad capacitors. And what we first did was to replace these two capacitors in series by an equivalent capacitor, because this one is the easiest part to simplify, and replace this one with your 4 microfarad capacitor or 4 microfarad capacitance, and we're just left now with 4 capacitors in your network. And the next thing that we did was to simplify these three, which are in parallel, and this three has an equivalent capacitance of 18 microfarad capacitance. And then we're just left now with two capacitors which are in series, and we replace these series capacitors by an equivalent capacitor of equal to 6 microfarad capacitance. So this is how you're going to get the equivalent capacitance of your capacitors in a network. So it's just a combination of your capacitors in series and parallel, and you do it until you end up with just one equivalent capacitor. So let us have another example. This is finding individual charge stored and potential difference in your capacitor network. For the system of capacitors shown in the figure, a potential difference of 25 volts is maintained across terminals AB. What is the equivalent capacitance of the system between A and B? How much charge is stored by the system? And how much charge does the 6.5 nanofarad capacitor store? What is the potential difference across the 7.5 nanofarad capacitor? For this problem, we are asked of the equivalent capacitance of the system of 5 capacitors, and we're also asked of the charge stored by this system. And lastly, we're asked of the charge that the 6.5 nanofarads capacitor store, and also the potential difference across the 7.5 nanofarad capacitor here. So in solving this one, we just remember that for your capacitors in series, the charge is the same in your capacitors, and for capacitors in parallel, the potential difference is the same in your capacitors. So we're going to use that concept to find for the charge that the 6.5 nanofarad capacitor store, and then the potential difference across your 7.5 nanofarad capacitor. So let's solve for the first problem. What is the equivalent capacitance of the system between A and B? So what we are just asked is to find for the equivalent capacitance of this 5 capacitor network. And as you can see, the first system that you can actually simplify is these 3 capacitors here, which are in series. So this is the easiest part. And you get to have these capacitors. Okay, let's just redraw it. Another one, and then you have this one. So this is your points A and B, and then this is your 7.5 nanofarads capacitor. We have here your 6.5 nanofarads capacitor, and then this is your, let's call this one as your C prime. Okay, so which is your C prime is a combination of, or as an equivalent capacitor of 3 capacitors in series. And we got your 1 over C prime, that's equal to 1 over 18 nanofarads plus 1 over 30 nanofarads plus 1 over 10 nanofarads. And this is equal to 17 over 90 nanofarads. And to get for C prime, we just take the reciprocal of your 7 over 90 nanofarads, and that is equal to 90 over 17 nanofarads, which is equal to approximately 5.3 nanofarads. And the next thing that you can do is to simplify these three, which are in parallel. So since these three capacitors are just in parallel, so your C equivalence is equal to 7.5 nanofarads plus your C prime, which is 5.3 nanofarads plus 6.5 nanofarads. And you finally get the equivalent capacitance, which is equal to 19.3 nanofarads. So this is the equivalent capacitance of the system between A and B. So again, what we did was we first simplified these three, which are in series, and then we are left with three capacitors. And these three capacitors are capacitors which are in parallel, so they're parallel to each other. And we got the equivalent capacitance of just one capacitor, that's equal to 19.3 nanofarads. Now let's proceed to the next problem. How much charge is stored by this system? That is, whereas of the total charge Q that is stored by this five capacitor network. So earlier we were able to simplify this 5 capacitor network into just one capacitor, which has this equivalent capacitor of just one capacitor, which has a capacitance of 19.3 nanofarads. So it's just saying that what is the charge stored by this 19.3 nanofarad capacitor. Okay, so here your Q total, or the total charge stored, is equal to your C equivalence times your voltage, which is, you have 19.3 nanofarad times your voltage, which is 25 volts. Okay, so this is straightforward. You get to solve for the total charge stored, that's equal to 482 nanocoulombs. So as you can see, we did not anymore convert your nanofarads into farads, because we can actually just use it directly. And instead of having your coulombs, we can use your nanocoulombs. Okay, so this is the total charge stored by your 5 capacitor network, which we did solve by just using your equivalent capacitor, which is your 19.3 nanofarad capacitor. Now let us solve for the last problem. How much charge does the 6.5 nanofarad store? And what is the potential difference across your 7.5 nanofarads capacitor? So we are asked here of the Q for your 6.5, and we are also asked of your V, your potential difference at your 7.5 nanofarads capacitor. Okay, so in order to solve it, let us go back to what we did earlier in the first two problems. So we first looked for the equivalent capacitance of your 5 capacitor network, and we had this diagram. So you have here your points A and B. This is your 7.5. This is your 5.3, and then this is your 6.5. And you can simplify it further into just one capacitor of capacitance 19.3 nanofarads. Now let us remember that for your capacitors in series, Q is the same, and for your capacitors in parallel, V is the same. If you're going to look at here, at this point here, the potential difference that is applied between points A and B is equal to 25 volts. Okay, so that means the potential across your 19.3 microfarad capacitor is equal to 25 volts. But if we go back higher, your 19.3 nanofarad capacitor is composed of three capacitors that are in parallel. So you have your 7.5, your 5.3, and your 6.5 nanofarad capacitors. And we said that for capacitors in parallel, your V is the same. So that means this 25 volt potential difference across your 19.3 nanofarads, which is composed of three capacitors that are in parallel, means that around your 6.5, your 5.3, and then your 7.5 nanofarad capacitor, the potential difference is equal to 25 volts. Because again, that is because for capacitors in parallel, the voltage is the same. So that means the voltage at your 7.5 nanofarad capacitor is equal to 25 volts. Now, we are just left of the charge that is stored at your 6.5 nanofarad capacitor. Okay, and we know that the voltage at your 6.5 nanofarad capacitor is equal to 25 volts. And Q is equal to your capacitance times your voltage. And here you have the capacitance of your 6.5 nanofarad capacitor times the voltage at your 6.5 nanofarads capacitor. So you have a capacitance of 6.5 nanofarads times the voltage, which is at 25 volts. Okay, and this is straightforward. So that means the charge at your 6.5 is equal to 162 nanocoulombs. So we're able to find for the voltage at your 7.5 nanofarads, and then the charge at your 6.5 nanofarads capacitor. Now, I will be giving you this as an assignment to find for the charge and the potential difference across your 18 nanofarad, your 30 nanofarad, and then your 10 nanofarad capacitors. Just do the same. Remember that for capacitors in series, Q is the same, and for your capacitors in parallel, V is the same. For the energy stored in a capacitor, what we meant is your potential energy that is stored in your capacitor. The potential energy U is just your Q squared over 2C, which is here your Q is your charge and C is your capacitance, which is also equal to 1/2 CV squared, where here your B is your potential difference, and this is also equal to 1/2 QB. When Q is in coulombs, C is in farads, which is also equivalent to coulombs per volt, and B is in volts, which is equivalent to joules per coulomb, your potential energy U is, of course, in joules. And this is how you look at the capacitor. The capacitor energy stored in the electric field between your parallel plates. So you can use any of these expressions to solve for the potential energy stored between your parallel plate capacitors. Now we can also think of the capacitor energy stored in electric field between the plates as the energy that is being stored in the field in the region between the plates. And we have this what we call your electric energy density in a vacuum. Vacuum meaning we don't have something in between these two plates. And the electric energy density, your small u is equal to 1 half epsilon naught E squared, where your epsilon naught is your permittivity of free space, and then your E is your electric field. So this is how you get for the electric energy density in a vacuum for your capacitor. If you can remember, there is this insulating material in between your two conducting plates, which form your capacitor. And we usually put your, or we usually call this insulating material as your dielectrics. When we say a dielectric, this is a non-conducting material, and most capacitors have dielectric between these two plates. So this is how you look at your capacitors, and then in between it, you have a sandwich material, which is your dielectric material. So this dielectric material separates your two capacitors so that they won't touch each other. Your dielectric increases the capacitance and the energy density by a factor of K. So if you're going to engineer your capacitors, it's not just the area and then the separation distance that you can change, but you can also change, or you can also put there some dielectric material which can increase the capacitance and the energy density by a factor of K. The dielectric constant of a material is your K, that is equal to your C over C naught, where your C naught is your capacitance without the dielectric, and then your C is your capacitance with a dielectric. And your K, that's always greater than 1. And the dielectric produces the E field between the plates. So for fixed voltage, you have also more Q that can be stored between your plates. Your dielectric reduces the voltage between the plates with fixed Q on its, which is again, remember that your Q is equal to um, your capacitance times your voltage. Okay, so this is what happens when you have your dielectric in between your two parallel plates. These are some of the dielectric constants. For a vacuum, meaning there's nothing in between your two capacitors, you have a dielectric constant of 1. And as you can see, if you're going to put or insert a dielectric, even just air, you're increasing the capacitance of your capacitor. And the best thing that you can actually put there is your strontium titanate, which has a dielectric constant of 310, which significantly increases the capacitance of your capacitor. Your dielectrics increase the energy density of your capacitor. Okay, as you can see here, because of this uh, K, which you are adding to your capacitor system. Now, if you're already inserting there a dielectric material, then we are not anymore going to use your permittivity of free space because it's not anymore vacuum, so it's not anymore free space, and we will use the permittivity of your dielectric. The permittivity of your dielectric is equal to your epsilon. That's equal to your K times your epsilon naught. As you can see, if you have your vacuum, your K is equal to 1. So we just use your permittivity of free space. But if you have your strontium titanate, for example, you multiply your permittivity of free space epsilon naught with your constant 310. And the electric field, when your dielectric is present, becomes your electric field is equal to your sigma, which is your surface charge density, divided by your epsilon. And for the capacitance of a parallel plate capacitor where your dielectric is present, you have your C, your capacitance dielectric, where your dielectric is present. That's equal to K times your C naught. C naught here is your capacitance when there is no dielectric in between your plates. And this is equal to, your C naught is equal to epsilon naught A over D. So what happens with your capacitance is that you have some K that's multiplied to your initial capacitance. Or this is equal to your epsilon. times A over D. Here, your epsilon is equal to the permittivity of your dielectric again, which is equal to K times epsilon naught. And for the electric energy density, when the electron is present, you have your small q that's equal to 1/2 K epsilon naught E squared. So we're just actually inserting again or multiplying your constant K into your equation. Please remember that your capacitors has this what you call your working voltage. Like say for example for your 220 microfarad capacitor, you can buy it with a working voltage of 25 volts. And you see that if the electric field is strong enough, there is this dielectric breakdown that occurs and the dielectric becomes a conductor, meaning your conductor is destroyed. The dielectric strength is the maximum electric field, which is in this case the voltage that the material can withstand with before breakdown occurs. And the table here shows some of the dielectric strength of some insulators, okay, which you can use as a dielectric material for your capacitors. So we have your polycarbonate, your polyester, and then your polypropylene, your polystyrene glass, and then your Pyrex glass.